guys, welcome back to MRWC. We're going to work on Activity 5C1 some more. This is the fourth video in the installment. I've already done 3 others on this. And so let's get going. Number 3 says, choose any 2 complex numbers, z sub 1 and z sub 2, and show that the following statements are true for those numbers. Then, prove that the statements are true for any z sub 1 equals a plus bi and z sub 2 equals c plus di. Wow. Why don't you make it any easier? Come on. Alright, well, let's look at this. So, sometimes we read stuff like that and it sounds a little intimidating, and you can let that scare you away, or you can just kind of dive in and just go for it, and maybe things won't be as hard as you fear that they are if you just try some stuff out. And that's always my go-to advice. Just try some different things and see how that works for you, and maybe then the question will make more sense to you. So this little bar above this z sub 1 here, that means, so z sub 1 here is a complex number, and the same thing with the bar on top, that means it's the conjugate. So let's say that we have, let's just say, for example, that z sub 1 is 2 plus 3i. Well, then that same thing with that little line over the top, okay, that's going to be 2 minus 3i. And we're just going to use this example to kind of work through this problem. Let's zoom in a little bit more. So let's try adding them up, because it says to add them up. What do we get? Well, what we get is we get z sub 1, right? So that's 2 plus 3i plus this part over here. I kind of wish I'd use a different color, so let me just do this. 2 minus 3i. I'm not going to worry about the other one for now. And if I add that, then I add the real parts. The real parts are going to give me 4. And the imaginary parts are going to add up to 0. So this is a real number. Okay. Do I have to show another example? Not really. So it says, then prove the statements are true for any z sub 1. And again, you don't really have to try a different number, because 1 will be enough. So let's, instead of 2 plus 3i, let's use a plus bi. So let's say I have z sub 1 equals a plus bi. Well, then the complex conjugate of that is going to be, you know what, the color thing. It's better this way. Z sub 1 equals a minus bi. And if I add these two together, I get a plus bi plus, oh, I forgot to put the line over it, thank you, a minus bi. And what do they add up to? This adds up to 2a. And remember that a, by definition, is purely real. I hope you all understand me. So, therefore, if you add a complex number and its conjugate, you will end up with a purely real part. Because of course you do. Because the imaginary part is simply the opposite. It's simply the negative version of the other one. So, of course you're going to add up to 0. So when you add them up, the imaginary parts go away, and you're left with that. Well, similarly, when you subtract them, the real parts will go away. So I'm going to go ahead and just skip to the a plus bi part. So if I have a plus bi minus the conjugate, A minus BI, right? What do we get? Well, I could do this all at once, but let's be nice and clear and thorough. This is A plus BI minus A plus BI. Because that negative, of course, distributes and flips those signs. Now when I combine these, I end up with 2BI. And that, my friends, is just a pure imaginary number. But Mr. Sandberg, there's a 2 in front. How pure is it? What that means is that it's on the imaginary number axis. Okay, so if you think of the complex plane, and instead of x and y axes, we have real and imaginary axes. This number is on the imaginary axis, and that's why we call it a pure imaginary number, because we don't have to add it with some real number. Okay, it's on the imaginary axis. Whew. Okay. All right. Other ones here. Z sub 1 plus Z sub 2. So if you add them, it's the same thing as adding the conjugates of the original. Let's go ahead and try that out. So let's say that we have A minus BI, so that's what they're saying, plus C minus DI equals Z sub 1, the original without the conjugate. So that would be A plus BI. And then plus this part here, C plus DI. But we're not done here. We have to take the conjugate of this. But what is the conjugate of that? Well, we're going to have to subtract the imaginary parts. If you think, I'll have to rearrange this. In fact, let me do that right here. So what I'm saying is that the real part, if I take this here, let me actually keep the colors. Maybe that'll make it more understandable. If I go A plus C, and this is my real part, all right? So this is my real, my A value, so to say, even though I already used the letter A. Minus BI, well, BI here is BI plus DI. Right, so now I'm going to subtract the imaginary parts because that's what that is. Okay, so this right here, what I'm trying to say is that. And I didn't do a good job with the color coordination. This was supposed to stay purple. It maybe would have helped if I had done this. Okay. All right. Now, is that true? Well, let's compare. Let's compare this with this. What do we got? Well, we have an A. That's the same. We have a minus BI. That's true. We have a plus C. That's true. We have a minus DI. Yep, they're the same. So, therefore, we've proven it for any complex number, Z sub 1 and Z sub 2, that if you add the conjugates, it's the same thing as taking the conjugate of the sum. Whew. Lovely. Number D, letter D, number letter D. What about multiplication? So if Z sub 1 is A plus BI, then the conjugate of that is a minus bi. And we're going to multiply this by the conjugate of z sub 2. So this is c minus di. And this has to equal those originals, so a plus bi, times c plus di, and then you take the conjugate of that, of all this. So let's simplify this right side here a little bit more. If you multiply these, if you just FOIL these, you're going to end up with AC plus ADI plus BCI minus BD. And I could rearrange this and simplify it, but let's just do the same thing for this one over here on the left. If I FOIL this, I get AC minus ADI oh, I forgot to finish this part over here. I do actually have to rearrange this. So let me stop. Let me go back to this part right here. So if I take the real parts, AC minus BD, I get AC minus BD. And then the imaginary parts are going to be plus I times AD plus BC. And so now, but they want the conjugate of this, right? So they want us to subtract this. So instead of adding this, we're supposed to subtract the imaginary part. And so all this is fine as long as I just remember that I hadn't taken the conjugate yet. Okay, so now I can go back to finishing what I was doing over here. So let's FOIL this. So I get AC minus ADI minus BCI plus minus BD. And now let's compare this and see if this is equal to this. So we both have an AC, yep. We both have a minus BD, yep. We both have a minus ADI, yep. And we both have a minus BCI, yep. Those are the same, hooray. We proved the thing. And we did what they wanted. For what complex number does Z equal the conjugate? Well, that's easy. So let's say you have A plus BI. Well, what they're saying is that this equals A minus BI. So how could that be true? Well, let's combine like terms. Let's subtract A on both sides. And let's add BI to both sides. So you get 2BI equals 0. Divide, well, I think it's pretty obvious. It has to be 0, right? So in other words, the the imaginary part has to be 0. So think of it another way. if you have some a plus bi, that's like this number here, the conjugate is just going to be the mirror image. It's going to be the reflection. So if this right here is a plus bi, then this right here would be a minus bi. And so, in other words, where is there no reflection? Well, if it's anywhere on this axis, and that happens to be the real axis, so in other words, it has to be a purely real number. So, yeah. All right. Well, I hope that was helpful. That was really dense. Thank you for paying attention. Hopefully you learned a little something about complex numbers and their conjugates and how they kind of work together. Thank you for watching. Please like, share, and subscribe. And consider buying my merch if you want to look cool. Thank you very much. Have a good day.